Hello everyone, welcome to KeAi Talks. Today's webinar is organized by Emerging Contaminants, and there will be 3 talks this afternoon. First, let me give a brief introduction to the journal. Emerging Contaminants is an outlet for world-leading research addressing problems associated with environmental contamination caused by emerging contaminants and their solutions. We have 2 editors-in-chief, Professor Gang Yu from Tsinghua University and Stuart Harrod from University of Birmingham in UK. Emerging Contaminants is an open access, high quality, peer-reviewed journal funded by Excellence Action Plan for China's STM journals. It is indexed in Biosys, one of the database of Web of Science, and Scopus. So in the recent years, the site score of the journal has been increasing. The latest site score is 9.7. The journal enables fast publication. You can see from here that it only takes 3.7 weeks from time to first decision, and it only takes 2.3 weeks from acceptance to the publication of the final version. So this is really fast. And after publication, articles are available at Science Direct, which enables worldwide distribution of the papers. We are now organizing some special issues from the paper you can see from here, Emerging Contaminants Control and Emerging Investigator, and also Legacy and Emerging POPs. So you are very welcome to submit to these special issues if you have some suitable work. Okay, let's talk about our webinar today. So the topic is environmental contaminants and the health implication. I think this is a very important topic for our human beings. And this webinar will be chaired by Professor Guorui Liu. He is the Associate Editor of Emerging Contaminants. Professor Liu is from the Research Center for Environmental Sciences, Chinese Academy of Sciences, and also School of Environment at Hangzhou Institute for Advanced Study, University of Kass. His research field is focused on analysis, formation mechanism, and control of persistent organic pollutants and persistent free radicals in the environment. So now I'm hand over to Professor Liu to chair today's webinar. Professor Liu, please.
Okay, good afternoon and good morning to Roland and other colleagues. And thanks very much for the introduction about the webinar from the KeAi Publishing. Thanks, Joy, for the introduction. As Joy introduced, there are many complex interactions between human activities and the environment and human health. And human activities could lead to the changes of environment and there's the health effects. Today we have 3 speakers and include 3 different types of pollutants was included in our free webinar. The first speaker, Roland Weber, will talk about the emerging persistent organic pollutants, and the second speaker from the Peking University will talk about the traditional pollutants, particle matters, and the health as well as the energy transition due to the human activities. And the third speaker will talk about the new contaminants, environmental persistent free radicals. So I think this free webinar will be very interesting to many different audience. The first speaker, let's welcome the Dr. Roland Weber. The topic about the the topic is the clean material cycles for circular economy. As we all know, Roland Weber is the environmental consultant. He has done over 28 years studies on the persistent organics. He has worked as an international consultant for the UN organizations, for example, the UNEP, UNIDO, and the UNDP. So he make very great contributions to many countries in their the national implementation plans for POPs reduction and control. So let's please join me to welcome Roland to give us the topic. Roland, please.
Yes, now you need to give free the screen that I can share.
Please.
The screen. Yeah, so thank you very much for invitation to Professor Liu and also to Zoe from Emerging Contaminants. My talk today will be on clean material cycles for the circular economy, learning from the challenges with polyprominated diphenyl ethers, the need of urgent control of chlorinated paraffins, and in the last slides I will come to many more challenges ahead. The first, when we look into the world, we see that we have not clean material cycles. This becomes especially eminent when we see the pollution, especially here in Asia, Philippines, Indonesia, of the marine plastic, and that our increasing production and consumption at the moment is linear and leads to a real waste and plastic nightmare. Maybe one positive thing is that this year UNEP, the United Nations Environmental Assembly, concluded to establish a plastic convention, but this will take time. And today I will also show you some more challenges when we talk about circular economy and plastics. So considering the waste crisis, what we have, and the limit of resources, humanity need to move to a more circular economy or circular economy. But when we move to a circular economy, we need to think about the fate of hazardous chemicals and materials, that they do not come into the wrong uses. And persistent organic pollutants, where I will give some insights today in the material cycles, are one of the problematic POPs and of the problematic chemicals. And we can learn for other chemicals. So when we move to a more circular economy, POPs and other hazardous chemicals need to be controlled and phased out. So first here, the first part is on the PBDE. So why do we need to assess and phase out POPs in products as soon as possible? Because some of these POPs are still produced, including productions in China. And here I start with the case of PBDEs in plastic. So polyprominated diphenyl ethers, or short PBDEs, are industrial chemicals which have been widely used as additive flame retardants since the 1970s in plastics and synthetic fibers, in vehicles, in electronics, in buildings, in textiles. And there we have a huge stockpile. They were produced in 3 different degrees of bromination. So products were commercial penta-BDE ether, stopped 2005 for the production, commercial octa-bromodiphenyl ether, which also stopped around 2004 worldwide. And we have the commercial deca-bromodiphenyl ether, which is fully brominated here. And this is still produced. This webinar is also, let's say, on human health effects. So therefore, I also give a short overview on relevant health effects here for the PBDEs and also afterwards for the others. So we have many adverse effects which have been associated with exposure to PBDEs, including endocrine disruption, reproductive effects, diabetes, and especially effects on the child and fetal neurodevelopment. So here the PBDE exposure adversely affect the developing nervous system in children. And here children in the US with higher PBDE levels showed 5 to 8 points lower IQ scores. Also in Dutch children, the prenatal exposure of penta-BDE and hexabromocyclododecan was also associated with significant adverse effects on motor, cognitive, and behavior outcomes. And a Japanese study reported that elevated blood levels of PBDE 153 correlated with the decrease of sperm counts and the decrease of testis size. So that's really worrisome and one driver why we need to phase them out. When we come to the DECA-BDE, the toxicity is lower, but DECA-brominated diphenyl ether is deprominating to the lower brominated PBDEs, which are more toxic, and also has a very strong potential to form brominated dioxins and brominated furans. We have done an assessment of the amount of brominated dioxins we have likely from PBDEs. So overall, we have about 1.5 million tons PBDEs produced in history. From this, about 1.3 million tons of DECA-BDE. And according to our studies on e-waste plastic and the content of PBDEs and the content of brominated dioxins, we can roughly estimate that from PBDEs, we have about 1,000 tons of brominated dioxins and furans in products. Yeah, and today in the plastics and in recycling partly. Yeah, so this shows the dimension, because normally when we talk about dioxins, we talk about micrograms or milligrams or nanograms. Yeah, but here we have about 1,000 tons just from the PBDE production. And an impressive experiment was from a friend of mine, Professor Vetter from Hohenheim University. So he put a bit DECA-BDE into a fish and then he cooked the fish. And what you see is that during the cooking, the DECA-BDE was decreasing here by about 80%. After the cooking, the DECA-BDE has decreased. So it has produced lower brominated diphenyl ethers and at the same time brominated dioxins. Yeah, so here about 3% of the DECA-BDE has been transformed to the heptafuran and about 1% to the hexafuran. Yeah, so you see that the DECA-BDE also cannot only be assessed by its own risk, but you need to include the degradation and the transformation to the dioxins. And that was the reason that in 2009, first commercial penta-BDE and in 2009 also commercial octa-BDE, there the hexa and hepta-BDE homologues have been listed in the Stockholm Convention, and later on in 2017 also commercial DECA-bromodiphenyl ethers have been listed in the Stockholm Convention in POPs, all in Annex A for phase out. Additionally, also hexabromocyclododecan as a brominated flame retardant and hexabromobiphenyl has been listed in the Stockholm Convention. So when they have been listed, this means tetra, penta, hexa, and hepta BDE in 2009, at the conference of parties, then some countries said, oh, but what happens when we list now the PBDEs in the Stockholm Convention? What happens with recycling of the e-waste plastic? Yeah, there we still have the PBDE in. And therefore, the Stockholm Convention finally decided in the listing that the recycling of PBDE containing polymers were exempted. But then in 2017, when DECA-BDE has been listed in the Stockholm Convention, there was no request on the recycling of PBDEs. And I think because over these 8 years, we have seen what kind of challenges we have when we recycle the PBDEs back into products. So when we look here for the PBDEs in respect to human exposure, we see that from production products, finally we have the reservoirs, we have thermal processes, and here from these processes we have releases into the environment. Yeah. Also here Professor Liu has studied on metal recycling and the release of PBDE from metal recycling. I have written a review article on POPs in landfills, where you see that they are released from landfills. And then we have the products. And before, with the old POPs, normally you were always talking about exposure from PCBs or exposure from dioxins, about this environmental cycle, the accumulation in animals, and then the main exposure via food ingestion. This is not true for the PBDEs. For PBDEs, for sure in China, also occupational exposure might be relevant, but for the whole world, the exposure directly from the products, for indoor consumers, and additionally from recycled products are relevant, because with the recycled products, we get the PBDEs back. And this we see with a range of studies in the past 15 years. Just a few examples. One of the best studies come from China, from South China, from Chen et al. 2009. He analyzed a range of plastic toys in China, and he found in all plastic toys he analyzed, he found PBDEs and other brominated flame retardants. Yeah, and showed that this comes from recycling of plastics. Yeah, but also here from for our countries in the US, PBDEs in polyurethane foam is recycled in carpet padding with high levels of PBDEs in recyclers, and those guys which are putting the carpets, the carpet installers. This is a picture from a coffee cup from Czech Republic. They have analyzed coffee cups, and especially here the black coffee cup lids, and a range of these coffee cup lids had PBDE levels up to 1000 ppm of PBDE. So directly when you drink your hot coffee, you can get a little bit extraction sip by sip. This is Professor Miriam Diamond from Toronto University. She screened her kitchen tools. And what you see here in this kitchen tool, she found about 1000 ppm of PBDEs, but also lead. So when you make these are salad servers. So when you make a salad afterwards, with the oil, you can extract the PBDEs, and with the vinegar, you can extract the lead. So this showed over the last 15 years that the recycling flows for PBDE containing plastic seems largely uncontrolled and need a better life cycle management and control. So the recycling sector needs considerable improvement and best available technologies, best environmental practice for separation of problematic materials. And I am very happy that the PBDEs came into the Stockholm Convention, that we can address this on global base. Another example of contaminated kitchen tools, and an experiment here from the group of Professor Stuart Harrod, who is editor-in-chief of Emerging Contaminants. So here they analyzed kitchen tools, and then they used this kitchen tool and put it in hot cooking oil for 15 minutes. And what you see is that already after 3 cookings of these kitchen tools, the low brominated PBDEs were completely extracted out of the plastic. Yeah, and for the higher brominated, it takes more time. This means here 3 servings, 3 times extraction with cooking oil, about 20% of the PBDEs were of the DKBDE was extracted. Yeah, but so you see how these PBDEs from the plastic finally also find their way to humans. Another very important consideration in respect to recycling is the lifespan of the products. So yes, we have stopped the PBDEs in the penta and the octa in 2009 here with the Stockholm Convention. We have stopped the hexabromocyclododecan in 2013. We have stopped the DKBDE partly in 2017, but DKBDE still have exemptions and can continuously be used in a range of exemptions. And when you have these products produced, here, for example, for televisions, it might take more than 20 years that the plastic finally come back into recycling. And when it's recycled, it goes in new recycled products and might have more 20 years of lifespan. So by this, you see, yes, even if we have stopped now the production and use of these PBDEs, still they will be more than 40 years with us. With the hexabromocyclododecan and polystyrene, it's even longer because this polystyrene is in building insulation. So here we are talking about a lifetime of 50 or 100 years. So when we talk about circular economy and these brominated flame retardants from the past, we have to think still the next decades and even century about they are present in the recycling cycles. But we need to recycle e-waste plastic. E-waste plastic is a super material. That's a slide from Chris Luikhaus, from the largest, one of the largest e-waste recycling facilities in the world in Austria. So he highlighted that the advantage of e-waste plastic recycling is that we have growing supply, and actually it is for free. People are happy if you take the e-waste plastic and recycle it. Then they do not have to pay money for the incineration. This means this material is self-replenishing. It's a super business model. Then when we do this mechanical recycling of the e-waste plastic, it only takes about 10% of the energy compared to virgin plastic. It has less than 10% water consumption compared to virgin plastic. And it can save between 1 to up to 3 tons of CO2 per ton of plastic produced. So also from this environmental perspective, we have to recycle this material. And also when you look after separation of these plastic types, the quality is like virgin plastic. This means this company sell back the plastic to electronic producers like Philips, and they make new electronics out of it. Yeah, so it is a real sustainable business, but we still have these additives. Yeah. So what is with the additives? In this facility, for example, you have separation technologies, zinc float and different others. And also our Stockholm Convention, but Web guide describe these kind of technologies. I mean, how to separate these plastics. But what we see is when we analyze the PBDEs here in these separated plastic, yeah, after separation, we still have between 75 and 130, sometimes 200 milligram per kilogram of PBDEs. So is this a problem? Big discussion point, depends in what kind of plastic application it goes. So this is really something also for health assessment. And this is at the moment a big debate for Stockholm Convention and Basel Convention, because the Basel Convention set a low POP limit. And if a material is above this low POP limit, then this material should be managed in an environmental sound manner and normally destroyed. And at the moment for the Basel Convention, we have 2 low POP limits. So one is 1000 ppm proposed from the European Union and some other countries. And we have the 50 ppm suggestion. This comes from African countries, 54 African countries and some other stakeholders, including IPEN. So if 50 ppm would be set as low POP limit, even the BAT recycling in Europe with separation technologies would not be feasible. This means recycling of e-waste plastic would need to be stopped. So you see what relevance these legacy chemicals can have here in the recycling. Okay, coming now to the second, and for China, even the more important POP. These are short-chain chlorinated paraffins. They have been listed in 2017. And additionally, what we in last year, the medium chain chlorinated paraffins are proposed for listing in the Stockholm Convention. So shortly to the health effects, short chain chlorinated paraffins and also medium chain chlorinated paraffins are persistent, toxic and bioaccumulative. So for SCCPs, the short chain paraffins, they already have been agreed 2017 to meet the Stockholm Convention criteria, and also for the medium chain chlorinated paraffins, this year it has been agreed in January that they basically meet the POP criteria. Yeah, so they are bioaccumulative, they are carcinogenic in rats and mice, they are categorized as group 2B as possible carcinogen for humans. They show reproductive toxicity to mammals and birds. They have effects on the thyroid hormone system, which is one of our main endocrine system in the body. And also they have effect on the nervous system in mammals. They are toxic also to aquatic organisms and have, for example, neurodevelopmental toxicity in zebrafish. And because of that, already in the 1980s, some countries have started to regulate short chain chlorinated paraffins. Here you see the time frame, 1988. Canada put the short chain chlorinated paraffins on their priority list. Here in 2001, already Norway prohibited the production and use of short chain chlorinated paraffins, but also preparation containing short chain chlorinated paraffins. Around 2003 to 2004, the European Union more or less stopped all short chain chlorinated paraffin use. And then in 2006, short chain chlorinated paraffins were proposed for the Stockholm Convention. But it took about 10 years finally that short chain chlorinated paraffins was listed. Yeah, because there was a big debate. Yeah, is it persistent enough? Is the effects in remote regions enough for listing? But I mean, production has increased and increased, as you will see. And finally, 2017 was agreed to list short chain chlorinated paraffins. But at the moment, China and India, which are parties to the Stockholm Convention, have not yet ratified the short chain chlorinated paraffins. Yeah, also because of the big productions of chlorinated paraffins they have, and I will show it to you. Chlorinated paraffins are a real headache. They are a complex mixture. From industry side, they have some really positive properties. They are versatile mixtures. So we have here differentiation in the chain lengths. So we have the short chain chlorinated paraffins. They have chain lengths of carbon 10 to carbon 13. Medium chain chlorinated paraffins, MCCPs, chain lengths C14 to C17, and the long chain chlorinated paraffins with chain longer, 18 and longer. Chlorinated paraffins are produced with different degree of chlorination, varying between 30 and 70%. And so here, the variation option of the chain length and the chlorination degree make them very versatile and useful for a range of industrial applications. And today we have approximately 200 commercial chlorinated paraffin formulations in use. For Stockholm Convention, the listed short chain chlorinated paraffins have to contain at least 48%. And for the medium chain chlorinated paraffins, they need to contain in the proposal now, a POP proposal, so they are now not listed yet as a POP, they need to contain more than 45% of chlorine. But also chlorinated paraffin mixtures, which contain more than 1% of short chain chlorinated paraffins, are considered POPs or short chain chlorinated paraffin mixtures. Chlorinated paraffin mixtures are very complex. So here for short chain chlorinated paraffins, we have about more than 5,000 different congeners. Yeah, here you see for the different chlorination degree and for the different chain lengths, how many isomers. Yeah, So very difficult or impossible at the moment to assign individual congeners. So when the short-chain chlorinated paraffin were listed in 2017, many developing countries, including also transition countries like China, have asked for exemptions. And basically today in the Stockholm Convention, we have a wide range of exemptions, which include basically all major uses. So exempted are plasticizers in flexible PVC, but not for toys and children products, not allowed. For rubber in transmission belt, for fat liquoring of leather, lubricant additives, metal processing, metal cutting fluids, waterproof and fire retardant paints, adhesives. So they are all exempted in the Stockholm Convention. So therefore, short-chain chlorinated paraffins will likely be further produced, used and released. And like I said, India and China, the major producer, have not ratified the Stockholm Convention yet. Hence, we need an assessment of the current use and also assess the need and assess alternatives and substitution. So to the listeners here, please have a look into these questions, and I can promise you it's really an interesting research issue, a policy issue, and also an interesting issue for industry. When we look just shortly a few slides in the environment, we see here the levels are especially high in Asia and especially high here in India and China because of production and main use. In China, the levels in biota here, a study from Shanghai University with Professor Bergman. So they have found that when you put all POPs together, the chlorinated paraffin in some of the animals they analyzed here in the Yangtze River Delta had more than 90% chlorinated paraffin as POPs. Yeah, so you see here the relevance of this huge use. And when you look into the Arctic, here for the polar bears, you see that for several of the polar bears, the medium chain chlorinated paraffins are even higher compared to the short chain chlorinated paraffins. Yeah. So also from this perspective, you see, we have to think and address also the medium chain chlorinated paraffins and need to control it. Here, when you look into the marine biota in the Chinese Sea, and this is logarithmic scale, you see here, you see a very strong increase of chlorinated paraffins in marine biota before in the China Sea around your coast. And when we look to the life cycle of chlorinated paraffins, it is the same like with the PBDEs. We get a huge amount into products, and from these products and the recycled products, finally we get a large indoor exposure and also occupational exposure. Yeah, there is food exposure, but I think that this is not the major exposure pathway. In China, for example, there is a study, it was a recent PhD study on chlorinated paraffins in house dust. And there it was several hundred ppm, yeah, close to 1,000 ppm in the house dust. Yeah, so you see how much of these, especially via the PVC, goes into houses and construction, and finally then into human. And because they are persistent and they bioaccumulate, they are also transferred to the next generation by human milk. And this is the result of all POP analyzed in human milk from the WHO human milk study from 65 countries from 2000 to 2012. And you see that chlorinated paraffin is already top 2. Yeah, only DDT, which is in some African countries really high, is still a bit higher than the chlorinated paraffins. But I can promise you over the next few years, this will change. And maybe already if you would sample today, 2020 human milk in average in the world, chlorinated paraffin will be higher than DDT and is already higher than PCB. One thing what we need to say in respect to toxicity, they are certainly not as toxic as PCBs. So therefore, at the moment for human milk, still PCBs is a much higher concern compared to chlorinated paraffins. But when we look to the toxicity evaluation of chlorinated paraffins, for example, I am missing assessments, for example, on neurodevelopment of children. Yeah, and we always see also with PCBs over the years and decades, when more studies come up, we will see that we see normally that these POPs are more toxic, and after that, then that we need to reduce tolerable daily intake, for example, or reference dose. So therefore, I think it's very, very important and timely that you need to do more toxicity assessment in China on these chemicals. So why the chlorinated paraffins are so much increasing in the environment, you see with this production figure. So this is the production of chlorinated paraffins up to 2014. And you see over the last 15 years, the production is hugely increasing. And the main driver of this is the production in China. Yeah, you see here the gray is the production increase in China from 2005 around, where Europe, for example, is more or less stopping the chlorinated paraffins production. Also, America has phased out chlorinated paraffin production, and at the same time, China has increased the production to more than 1 million tons a year already by 2014. And I think now at the moment you have a production capacity of 2 million tons. In addition, India is increasing their production, and also they have a production volume, I think, which is more than 500,000. Yeah. So by this, every year we get 1 million or up to nearly 2 million tons of chlorinated paraffins more in our production cycle and more in the technosphere. This you can compare with PCBs. The total production of PCBs in history total was about 1.3 million tons. Yeah, so you see how much of chlorinated paraffins you have here. An estimate how much short-chain chlorinated paraffins, which are already POPs in these. There was an estimate from Klüge, so she estimated that about 20% of all chlorinated paraffins produced are short-chain chlorinated paraffins, and in 2016, she estimated that we have about 200,000 tons of short-chain paraffins per year. But when we look to recent analysis data from KeAi et al. From China, for the CP52, which is maybe nearly 90% of the Chinese chlorinated paraffins, she found in average 35% short-chain chlorinated paraffins. So this indicates rather that more than 350,000 tons of short-chain chlorinated paraffins are still produced in China. And China is not producing short-chain paraffins, medium-chain paraffins, but it's rather mixtures of short-chain and medium-chain paraffins. And this CP52, this is produced in around 900,000 tons and is normally a mixture. This means we have about 900,000 tons of SCCP containing CP mixture, which you are producing. So the big question is, where does this go? And there is a good study from Beijing University, from Chen et al. And he analyzed 124 product samples from markets from China. So here a high share of PVC, especially these curtains and sheets of rubber, but also polyurethane spray, which are also used indoor, with up to 30% and more of chlorinated paraffins in these products is produced. They found lower concentration, for example, in metalworking fluids or textiles. Yeah, but let's say for overall market survey, the 124 product samples are too less. So also I think here there is some real interesting research needs. And where do these finally end up, these products? Yeah, they also end up finally here in Germany. We analyzed our baking ovens. Also Professor Vetter, she analyzed 20 baking ovens. And in these 20 baking ovens, 50%, 10 baking ovens had very high chlorinated paraffins inside the baking oven in the fat. Yeah, so these were operating baking ovens. Up to 1% of chlorinated paraffin in the fat. Yeah, so this came from cables. So you put about 20% in the cables. These cables come into the ovens. In the ovens you heat it, and the chlorinated paraffins go out into the ovens and directly into the food. Yeah. So at the moment he's assessing how much is going directly into the food. But in the baking oven, the most cold thing is the food which you are baking in. Yeah? So therefore, most of the chlorinated paraffins will go into the food and not to the wall. Another example is food blenders, analyzed in Sweden, but also Shanghai University. So here they found that 8 of 12 food blenders were reaching high concentration microgram per gram of the food of 5 food blenders, yeah, at very high levels, and 3 others at lower levels. And here the source is also plastic parts and some lubricants which are kind of used in such. And what was very interesting, so they repeated the use of the blenders, and also after 10 times, the chlorinated paraffin release did not decrease. So this is rather from plastic parts. And if you have then a plastic part which has a weight of maybe 5 grams, yeah, or 3 grams, and you have 30%, so you can understand that for years you can reach here the chlorinated paraffins in the food. Interesting was also here the analysis of short and medium chain paraffins, and you see these are these mixtures which you find when you analyze the CP52. Yeah, so most of them you see here chlorine content 54, 55, 52, 56. So they're all CP52. Yeah, and probably mostly from China. We have unfortunately not much analysis of India. It could be that for India it's the same. So therefore, very important, and that's my main work, is to do inventories and to assess, like Beijing University has started. So we have here a guidance from the Stockholm Convention. And here the guidance proposed, please look to the additives in PVC production and an assessment into the rubber production and into rubber products, into paint production and paint use, into leathers, adhesives and textiles. So this is, I think, a very good research work for the future for some of you. And I think all sectors where these short chain chlorinated paraffins are possibly used in manufacturers should be assessed, and for the assessment industries and productions possibly used should be addressed. One is Chen et al. For China. We have done something similar for Brazil and published it. And also we have written a review article of chlorinated paraffin in the technosphere and published it in Emerging Contaminants in our special issue. And for the Stockholm Convention, I headed the pilot inventory, and the pilot country were Indonesia, Brazil, and South America. And here I show you some data from our first preliminary inventory for Indonesia, that you see the dimension. So here we have assessed PVC imports. And we have only assessed the PVC, the soft PVC, which have additives in imports. And what you see over the last 30 years to Indonesia, we have more than 1 million tons, close to 2 million tons of PVC containing additives. So this is the dimension finally you need to assess and to manage. Yeah. And then you need to monitor these products. This we have not done in these studies. And we need to look then to PVC recycling. Yeah. So like I showed you for the PBDE recycling. So that's the headache, which is in the future for us. The same, we have done the assessment Indonesia for rubber imports. Also here only for the rubbers which contain additives. This means not the rigid rubber, the raw product, but here, for example, conveyor belts, where we know that they contain flame retardants. And also here from these rubbers, we see that we have close to 2 million tons, including additives, imported to Indonesia. Yeah, and also here the question, okay, what happens then in recycling finally? So how much is total in these? Yeah, and what will be the limits? What will be the low pop limits? Yeah, big headache ahead, I can promise you. What you see with Indonesia, also Indonesia is importing rubber waste, pairings and scrap. This means in Indonesia is already recycling waste rubber. Yeah, so very important to understand where this waste rubber goes. We have analyzed in Europe rubber products, toys with rubber and PVC, and we find in many of these toys finally, chlorinated paraffins can come from the primary production, but also it can come from the recycling, what we see with the PBDEs. So therefore, when we look to short-chain chlorinated paraffins and the major use, we see that a range of recycling cycles are impacted. This includes PVC recycling, this includes rubber recycling, this will include also buildings and demolition waste from adhesives, from sealants, from PVC, also metal and cutting oil. This and lubricants will impact oil recycling, and also leather. The use on leather might impact the leather recycling. So here we have future recycling problems ahead, which we need to consider when we put more of these materials into products. One slide on total global containing plastics containing short-chain chlorinated paraffins or chlorinated paraffins and PBDEs, total amounts and future management needs. So here with chlorinated paraffins, we estimated that for China you have alone 900,000 tons per year which contain SCCP and MCCP. This finally will go into products like PVC and rubber. So here maybe you use in average 10%. This would mean every year from the 900,000 ton% of the CP mixture, you produce about 9 million tons of POP containing polymers per year. Yeah. So this will need to be managed in future and including the recycling. When we look to the PBDEs, we can estimate today we have about 53 million tons of e-waste, including about 10 million tons of plastic, because 50 million tons of e-waste, about 20% is plastic. So we have every year 10 million tons of e-waste plastic, which we need to manage and see how much we can recycle. Also, when we look to end-of-life vehicles containing these PBDEs, but also partly chlorinated paraffins, hexabromocyclododecan and PFOA, we have about 10 million tons roughly of polymers and plastic from end-of-life vehicles. And when we look to hexabromocyclododecan containing EPS and XPS, alone for China, you have EPS and XPS in construction in the 10 million tons scale up to 100 million ton scale. So these are huge POP containing plastic volumes which need global management efforts, not to further litter the world with plastic and POPs. In China, you have now a good project, interesting project on the HBCD phase out, and congratulations, last year, China phased out the production of HBCD, and this CHEF project with UNIDO and FECO, the environmental ministry from China, this has also a project component on end-of-life management of this HBCD containing plastic and polymers. And I think that this will be a very good opportunity, let's say, to put a standard approach for destruction. But in this project, we are considering to destroy about 1,000 tons of this HBCD containing EPS and XPS. Yeah, so this is only a ppm, yeah, of the plastic containing POPs which you have in your country. And there are more challenges ahead. We have more POP candidates which are additives in plastics. We have Decloran Plus, which is a flame retardant. This is currently in the POP reviewing process, but already closed. So maybe in 2 years' time, Decloran Plus might be listed as a POP. And we have the first UV stabilizer. Yeah, UV 328. It's also the first chemical which is not halogenated, which is proposed as a POP. So this is still in evaluation. So, but by this kind of impacted plastic will further increase. The same when you look to PFOS, PFOA, also a large share of them has been used in side chain fluoropolymers in surface treatment of textile, furnitures, and carpets worldwide. Not so much in China, more in America, in Europe. Yeah, so that also add to POPs in plastic. And now we have long chain chlorinated, the fluorinated carboxylic acid proposed as a POP. So also they will add. This means more POPs in plastic will be added to the Stockholm Convention and will result in even higher amount of plastic and polymers containing POPs and lead to higher share of plastic containing such POPs in recycling. And looking to the very big picture, we have at the moment a project for UNEP. And in this project, we evaluated how many chemicals are used in plastics. And the total amount of chemicals which are used as additive in plastic or which are used in production of plastics or known to be in plastics are around 13,000 chemicals. And about 2014 of these chemicals are substances of some concern, mean they already have one of the risk phrase in the GHS. Yeah. So yes, so with POP we understand how much we have problematic chemicals and especially how problematic it is to manage those when we talk about circular economy. But when we now consider the bigger picture of these 2,400 chemicals, yeah, we really need to think how to address it. Yeah, also think how to address it from risk, from risk and health exposure view. So here I see very much work, and I see that the industry basically the last 30 years slept. Yeah, because of course, yes, we as a researcher, this is a task for us. But basically, it is the big homework of the industry, because finally they have a producer responsibility. And if finally the waste cannot be managed by the normal society, the industry will have a responsibility of the management of these end-of-life products. Yeah. So therefore, here I see a big homework also for the industry, and also that the industry give more funding to research, to do an assessment, and to help to solve this kind of recycling nightmare the next 10 or 20 years. So one part of a solution ahead is that we substitute the most problematic chemicals. So here, this is, let's say, the substitution steps from Ken Geiser from the Lowell Center for Sustainable Production. So he said, first, we need to identify chemicals of concern. This part I have done in my presentation. And then as a second step, we need to select priority uses. And select priority uses, one is straightforward, are toys and food contact materials. So there is already much research ongoing, but also seeing what kind of challenges we have. Then we need to identify alternatives. And then we need to characterize alternatives, especially, and compare the alternatives. Especially this is important for a successful phase out of hazardous additives and not to do regrettable substitution. Because what we, for example, see with the PBDEs, the low brominated PBDEs have been substituted by high brominated PBDEs. Yeah. So that was a kind of regrettable substitution, and partly the PBDEs have been substituted by hexabromocyclododecan. And when we look to other PBDE, to other brominated flame retardants which are currently used, for example, there is octabromotoluene, there is hexabromobenzene. Yeah, they are certainly POPs. Yeah, but they are currently used as alternative. Yeah, so here we need to take care not to substitute with the wrong chemicals, and in 5 years' time have those chemicals listed. So here we need then to score the alternatives and phase in the most sustainable alternative solutions. And this we can best do when you look here to the so-called 9R process, yeah, in the production phase here in the redesign. Yeah, and I think also here this is a very big research area where when you put the right chemicals, sustainable chemicals with low toxicity, which can facilitate also recycling, this is a super interesting research area for you. Okay, yeah, thank you for your attention. Here is the link to guidance documents of Stockholm Convention, where you have inventory guidance for these chemicals, where there are BAT-BEP guidances, including guidance for separation. But also there are guidances on alternatives to the listed POPs. Yeah, so please have a look to them, and then we can move on and improve our material cycles.
Hello, Roland. Very nice presentation, and thank you very much. A lot of very important knowledge and very important information for our research and for the policymakers. And then the answer on the question in time. So Professor Guofeng from Peking University, please, your question.
Hi, Roland. Thank you for your talk. My question is that, is there any data or information about the degradation data about the CP or SCCP, and how it is compared to PCBs, for example?
I mean, they are less persistent. Yeah. Yeah. Also, I mean, one thing, the first thing you have to look into humans. So I think they are better metabolized. Yeah. But I mean, you see that they accumulate with the levels we have in human milk. And also there, you know, you have this very complex mixture. So I have not really seen very good studies, let's say, which show, okay, you know, with PCB, for example, we really know, for example, for the PCB 101, that already the chicken can metabolize it. And the pork can metabolize this and this and this. Yeah. So I think here there is a lag. I have seen one very interesting study also from China. They have shown the metabolism of long chain chlorinated paraffins, and in biota, long chain paraffins have partly been degraded to medium chain paraffins and short chain chlorinated paraffins. So I think, yes, we know a bit on this degradation. So they are less persistent than the PCBs, but I think we need to learn much more.
Okay, thank you.
Welcome.
Okay, we also have at least two other questions. The first is from Bingcheng. Bingcheng, can you ask directly online? Hi, Joy. Can the audience ask the...
Or you read the question.
Okay. The question is, we recently did a research on the emission of PBDE from secondary copper smelting industry, and PBDE can be unintentionally produced, and the amount, the concentration is high. So what is your opinion about the regulation of PBDE covered by the Stockholm Convention? Is there any possibility that PBDE was included in the Annex C in the future? What is your opinion?
Yeah, I don't think so about that they will be listed in Annex C. And you know, already by listing in Annex A, I mean, you could also prohibit the release of PBDE from those industries. Yeah, but in the whole world, I think I only know one regulation for PBDEs in emissions, and that's from Belgium. In Belgium, there is, for the permit setting of shredder plants, there is a limit for PBDEs in the air emission. Yeah, so here I think you might have a look to this regulation in Belgium. And then you can think if it's interesting or relevant that you set a limit for PBDEs also from smelters. You know, because the PBDEs and the chlorinated dioxins or PCBs, they behave the same. This means if you make a regulation for dioxins and for PCBs, and you minimize dioxins and PCBs, at the same time also PBDEs will be reduced from air emission. Yeah, so therefore I think that at the moment, the regulatory frame for chlorinated dioxins, if you set it to 0.1 nanogram and you have filters and so on, and active carbon filters or catalyst, this will also kill the PBDEs. In Europe, there is an attempt to address the brominated dioxins, because maybe in these thermal processes, when you look to toxicity, maybe the brominated dioxins or the mixed halogenated dioxins might even be more relevant than the PBDEs. So there was one attempt in one regulation to at least measure the brominated dioxins, but this has also not with a regulation limit. So at the moment in Europe, it's only that you have to measure every year also the brominated dioxins. So the European regulators want to understand what is the relevance. I think here also in China, you have good projects, a CHEF project coming for secondary metal industry. And I think here to think and in respect to regulation, should we include brominated dioxins, or how can we maybe address brominated, mixed halogenated, chlorinated dioxins together? And then also your question, do we need to do anything with the PBDs in emissions? I think this could be a research topic in that CHEF project of the secondary metal industry.
Okay. So, thank you very much. And a question from Dr. Liu. The question is about the balance of circular economy. Should we assess the environmental and economic cost from the whole life of the products, including production, storage, transportation, usage, disposal, and reproduction process? How to avoid the environmental and economic losses from recycling processes? Thank you.
No, I also think that the assessment need to be much more holistic. So a friend of mine, Peter Vanke, from Copenhagen University, DTU, so he is doing this life cycle assessment for chemicals. And so he thinks that already in this phase, this means the design phase, when you do a substitution of chemicals, you should do a much better and more holistic assessment of the chemical from its production, from its use, and also considering recycling and exposure. So here I think a better frame is needed. And at the moment, I mean, for our project HBCD phase out with MIFECO, there is also a project component for the assessment of alternative and to develop a better frame of the assessment of alternative. So I completely agree with you. We need a much better assessment of the chemicals when we do a substitution, and it should include the whole life cycle. And of course, we need to balance, let's say, risk of exposure and economic benefit or climate benefit, but of course not to bring the PBDEs into toys, but maybe to recycle them again into electronic products where in the normal use you do not have an exposure. And like I said here, we have much more homework from the industry to do these studies and to show this exposure, but also from the research community.
Okay. Thanks very much, Roland. And the last question is from your old friend, from Minghui, my group leader. I shared one slide in our research group. He asked a question. The question is, you mentioned SCCP is detected in the baking oven, right? In the baking ovens. SCCP in baking ovens. Yes. Yes. He wondered where the SCCP come from in the baking ovens.
Yes. So they come from plastic. So you know, you have in the baking ovens, you have cables, electric cables, and you have also, let's say, plastic parts in the electronics. Yeah. And so when you heat up the baking oven, you know, you heat it up 100, 150, 200, 220. If you make a pizza, you even heat it to 300 degrees. Yeah. And when you heat these ovens then to these high temperatures, then the additives come out. And when you look to this figure, so here you see on the top, wait a moment, I show the, with the laser pointer. So these are the chlorinated paraffins, and you see really 50% of the baking ovens have high levels of chlorinated paraffins, and 50% of the baking ovens don't have chlorinated paraffins. Yeah. But, and you see here up, this is close to 100, close to 10%, this one. Yeah. So this means 10% of chlorinated paraffin in the fat. Yeah. And it's mainly MCCP. Yeah. So maybe it could also come, I think that these chlorinated paraffins don't come from China. So maybe these chlorinated paraffins might come from Europe, because we are producing MCCPs. Okay. One thing. The second thing to this figure is that also for other baking ovens, we find PBDEs. So you see, especially those baking ovens which do not have chlorinated paraffins, there we find PBDEs. But the levels of the PBDEs are much, much lower. Yeah, you see here, nanogram per gram fat. This is about, let's say here, 5,000. Yeah, this one is the only one which is higher, this two. Yeah, so, and there you see that for deca-BDE or also for the octa-BDE, even at 150, 200 degree, the release is relatively low from electronics. Yeah, but the chlorinated paraffins have a much higher volatility compared to the PBDEs. Yeah, so this study is really interesting to have a look at.
Okay. Thank you very much, Roland, and really very
also,
nice.
Also, thanks for the interesting questions. Yeah, thanks, Minhui.
Yes. Okay. Let's move to the next speaker. The next speaker is Professor Guo Feng from Peking University. His topic is about the health and the climate benefits of particle matters reduction under the clean household energy transition. Please join me to welcome Professor Guo Feng.
Okay, thank you, Professor Liu. Share the slide first. Okay. Good afternoon, and maybe good morning or good evening for the people in the place of the world. So I'm Guo Fengshen from Peking University, and today I'd like to share you some of our research about the health and climate core benefits of particle matters reduction under the clean household energy transition. And today's webinar is about the emerging contaminants. So our group used to have some works about the POPs, and in fact, one of my PhD students is doing some work about PBDs, but we did not have results to show today. So I like to say today I like to show you some traditional non-emerging contaminants, probably non-emerging contaminants as a registration for this webinar, and hopefully we can have some results or some research results about the emerging contaminants later, and then we'll share you in the next in future. In fact, no matter emerging contaminants or non-emerging contaminants, one of the reasons that we focus or we study and try to control it is because it's harmful to our human health. So if we look at the exposure risk to human health, we can see that air pollution is one of the top environmental risk factors. This figure shows the rank of environmental risk factors in China. We can see the air pollution ranked the first, that's after the high blood pressure, tobacco, and So this is for China. If we look at the global average situation, it's also that air pollution is one of the top environmental risk factors. So this situation is generally true for most developing countries. Of course, we know that there are many different types of air pollutants. Today, we focus on the fine particle matters, and some studies focus on other air pollutants like ozone. But if we look at the per natural days due to air pollution, we can see that the largest number was due to the exposed to fine particle matters. Air pollution or particle matters can from many different sources. It's including power plants, industry, and also the household fuel combustion when you burn fuels for cooking or heating. So our research focus on residential, or some studies say to focus on household air pollution. This is because that different from the other source like industry or vehicles. Residential emissions produce air pollution not only to outdoor air, but more important to indoor air. If we include both indoor and outdoor exposed into the total exposed, we can see that, or some of our results show that the contribution of residential emission contributed largely to the total PM 2.5 exposure and contributed largely to the final per natural days. So my talk today were 3 parts. The first is about the residential energy consumption in China. The second is about its impact on outdoor air pollution. And then the third part is about its contribution to indoor air pollution. Globally, there was an estimate about how many people are using solid fuels. Solid fuels here means you're using coal or biomass. In about 2013, one study published in UHP estimated that globally about 40% of people is using solid fuels for daily cooking. And the number in China is about 48% in 2010. Just recently, last year, another new study published in Nature Communication estimated that globally now was about 30% of people using solid fuels for cooking. And of course, there are significant differences between urban and rural areas. They estimated that in future, even in 2013, there would be still about 2.7 billion people, because even though the fraction of people using solid fuels declined over time, but at the same time, because the population grows, the absolute number of people using solid fuels for daily cooking did not change very significantly. But we note that in such studies, one number they said the population mainly use or primarily use, but in some words or in some situations, people are confusing about the primary. What do they mean primary? Do they mean that you're using fuel in most of the time, or do they mean the consumption amount is the highest? So the reason we have this question is because we know in many places, most people using more than one fuels in their daily lives. You may burning wood or using electricity for cooking, but you may also burning coals for heating, and you may using electricity to cook rice. So in most households, people using more than one energies. We call this stacking. Energy stacking is very significant, not only in China, but also in many other developing countries or developed countries. We have a study show that in China from the 1992 to 2012, the fraction of people using multiple energies increased very significantly. But the earlier, there were for the household using only one energy types, they decreased from 28% to 10%. At the same time, the household using 2 or 3 energies increased very significantly. So there are many reasons behind this. One of the reasons is because the heating demands. In many places that people are using one energy for cooking, but using another energy for heating. And another reason is because of the income levels. With the change of the income level, the income, people may using less fuels to meet both daily cooking and heating demands. So in recognizing this, we think that the primary approach that may be did not accurately give us an answer how many people or how people using different energies in their daily lives. So in one of our study, we create a new terminal. We consider it a time sharing fraction. So we ask people different types of energies, usually in different activities, how long they used over a year or over the heating period. And then we use this number to see the structure of residential energy. Here is the results showing in the first national survey. It was in 2012. We can see that for cooking, that people are using gas or electricity for cooking in more than total is in more than 60% of the time. But for heating, electricity was used in about 15% of the time. And in the other time, people using solid fuels, coal or biomass for heating. And then after this, we did. So we compared these two approaches. One is only asking the primary fuels or ask primary plus secondary. And then another approach is that we said we use the time sharing fraction. We compared these two results from these two approaches. We found that if you using the traditional survey approach, you will overestimate the use of biomass. And another interesting result we saw is that if you using the primary or single fuel survey approach, you will estimate more extra energy use by 20 to 40%, which means you will overestimate the fuel consumption amount in the residential sector. So if we revisited this by correcting the multiple energy use, energy stacking, we saw that generally that more people is using clean fuels or clean energies in their daily lives. But at the same time, because of the rural, the people decreased due to the urbanization. But generally see that we found that more people using clean modern energies, which means here electricity or gas for cooking and heating over the past 20 or 25 years. This is the first study, national study we did several years ago. Just in about 3 or 4 years ago, we did a second national study. And then we saw that we can see a continuously increase in the using gas or electricity for cooking on a national average scale. And in 2017, we see that gas or electricity was used in more than 70% of the time. The increase was very obvious. And also at the same time, we also see an increase in using gas or electricity as modern energy for heating on a national average scale. This also increased, but the increases rates or the speed was very lower compared to that for cooking. And moreover, if we look at the spatial difference for clean cooking, we see 3 different types. One is in the south or in the central China. We see that there is a generally continuously increase of clean heating from 1992 to 2017. And then the second pattern is that in the northeast or northwest, that is most places in the north area, that the clean heating is very, very minor. It was less than 5% and it did not change very significantly. But the third pattern is here that I called it, this is due to the policy of clean heating. That we can see that before 2013 or 2014, the increase of clean heating is there was some increase, but it's a very slight, very small increase. But after the 2013 or 2014, after the national clean heating policy, that the clean heating fraction increased very sharply. So this is clearly show the impacts of the national official intervention policy on the clean heating in China. So we also estimated that in these areas, that when there were clean heating camping, some people may know this is called in some studies they call it coal to gas or coal to electricity policy. This policy is going to change from the coal heating to using clean ones. But we see that this policy also has some significant impacts on the clean cooking. in areas without national intervention, we predict value was close to the real measured values. But in those with clean heating intervention, we found that there was at least 10% more clean cooking fractions in these areas. But as I said, that what we show here is we use the time sharing fraction. So time sharing fraction is different from the solid amounts or the total physical amounts. So if we look at the physical amounts in units of mass or energy, still that we say that solid fuels, that which means coal and biomass, was still the main energy in rural China. In comparison, the data from between 2012 and 2017, we can see that people are using less coals, but the most significant reduction was found in biomass, especially those used for cooking has been changed very significantly. At the same time, people are using more gas for cooking in these 5 years. So also that this slide just shows some interesting results I participated, that which is leading by Professor Duan from another university. This shows the heating situation in schools. As most of my research focuses on the heating or cooking situation in rural households. So this is another place that especially many children stay there more time in schools. They found that in most schools in China, they use gas or electricity for heating, but still some place the solid fuels was burned for space heating. And the space heating was different between the schools and their homes, which means that for most of the children, when they come back to home, they were exposed to a different situation compared to that at schools. So this is the first part of our work. The second part is when we have information about residential energy consumption, then we studied its impacts on outdoor and indoor air pollution. So to do this, we needed to do some emission measurements, because with the emission measurement, we get emission factors. We have emission factors and they're multiplied by the fuel consumption amount. We can estimate the total emission amount. So I did this work since my PhD study, and it's already done for nearly over 15 years. So we tested different fuels, solid fuels, in different stoves. In some traditional ones, some many improved ones, and then we did this in library, and then we did this in field real-world conditions. So generally, we can see we found a very significant difference between different fuel and stove combinations. And generally, that biomass, that the wood and the crop straws had lower emissions compared to the bituminous coals, but it was higher than anthrax. We studied the particle mass concentration emission factors, but also its size distribution. And most of the particles were very, very small. And of course, the particle size distribution is different among different fuel and stove combinations. This is because they have different burning conditions. They have different stove types as well. And I'd like to talk a little more about one of the results I found very interesting. That is, we studied the emission of ultrafine particles from the cook stoves. We know the ultrafine particles is very small. Most of it was less than 100 nanograms. It may produce more health impacts compared to the particles, coarse particles. There was one study that it estimated the global emission of ultrafine particles. They found there are high emissions in most places. Of course, the emission in China, India are much higher than compared to other places. And different from the source of particle mass, that is the source of the ultrafine particles, normal concentration. The largest one is the vehicle emissions, and then the second largest is the power plants. The third largest is the residential. Of course, this is the global average situation. This is different in countries or in regions. So we have some laboratory studies about the ultrafine particle emissions from different stoves, burning in different fuels, burning in different stoves. Here we see that the green column is the emission of particle matters, PM2.5, and the circle here is the emission of ultrafine particles. Generally, they are positively correlated, but did not show the same changing rate. For some stoves, it has a very high particle mass emission, but relatively low ultrafine particle emissions. But for some stoves, it has a low particle mass emission, but it has a high ultrafine particle emissions. And if we look at the fraction of particles less than 30 nanograms in the total ultrafine particles, we can see that for some, we call it clean or low, high efficient, low emission stoves, which is, so for example, this is a wood burner in one of the forced draft stoves. Its particle matter emission was very low, but its fraction of small particles less than 30 nanograms was about 8% of the total ultrafine particles. This means the health impacts of these particles or particles emitted from these stoves may not decrease as large as that in particle mass. So, of course, we also have some other emission studies. For example, we recently published a paper about the emission about the EPFRs from the cook stoves. I know our next speaker will talk about the EPFRs. So based on the emissions, so a factor works, and the energy consumption data we collected. So we updated the emission inventory. This is the emission inventory work leading by Professor Tao from Peking University. This inventory that was open to the public free of charge. So if you need some emission inventory results, so you can go to this website, and then we have very high resolution results. We have the emissions from over, I guess maybe over 30 or 40 compounds from a global emission inventory. And we have a very detailed information about its fuel types, its sector information, and at a high time resolution. So for example, for PM 2.5, we can see that nearly 1/3 of the emissions was from the residential sectors. And for black carbon, and also the PAHs, nearly half of these emissions were from the residential emissions. Based on the emission inventory and by using the air quality, chemistry transport models, so we estimated the rural residential contribution to the outdoor air pollution. Our data showed that generally say that about 10 to 20% about the outdoor air pollution can be attributed to the rural residential emissions. This is our modeling work is for 2012, but I guess recently because of the clean energy transition, now this fraction decreased to 10% or around 10%. We said that we can see that rural emissions affect not only the air quality in the rural area, but also in the urban area because of the air transport. So, and of course, that's the national average. There are very significant temporal and spatial difference. In winter, the contribution would be higher, and in the place of the north area, and also in the southwest area, like the Qinghai and Tibet areas, residential emissions would be higher than the national average. As I mentioned, that from the 2012 to from the 1992 to 2012, in that 20 years, people have used more clean energies. So we estimated the health benefits during this clean transition. We estimated that in these 20 years, the PM 2.5 associated per natural days decreased from 570,000 to 200,000, which means that we have saved about 300,000 people due to the exposure from the residential emissions. But we know at the same time, because the population is growth and the population is aging, and also the mortality rates changed. When we adjust these factors, we still see a net about 130,000 per natural days avoided due to the clean transition. This is the health benefits. At the same time, we also see a significant climate core benefits because during the clean transition, we saw a significant reduction in emissions of black carbon and organic carbons, organic aerosols. And this reduction will result in a net decline in the forcing of the climate. So we can see that during this transition process in rural areas, there were significant health and climate core benefits. My work mainly focuses in rural areas. And our research group, a big group leading by Professor Dao, also did some interesting work about the urban residential energy transition. This slides show one of the results recently published. So we saw that from the 1980s to 2000, in that 20 years, the urban population in China increased by 1.5 times. But at the same time, the energy consumption increased only by 10%. This is because more people are using gas or electricity, those high efficient modern energies. So at the same time, they discovered that most air pollutants emission decreased and the air pollution reduced. And this urban residential energy transition resulted nearly 2.2 million per night days avoided during the 20 years. This is urban residential energy benefits. Now, as I mentioned earlier, our work focuses on residential energy is because it affects air quality not only outdoor but also indoor. And in fact, it has a more direct impact on indoor air quality. So research on indoor air pollution or household air pollution in China was relatively less compared to that in outdoor air pollution. There were some studies during the 1980s, but after the 1990s, there were much less studies. Since the early of this century, there were more studies, but still much less compared to the outdoor air pollution. We're concerned about the indoor air pollution because most people spend more time indoor. And in most cases, indoor air pollution was serious compared to outdoor air pollution. I mean, especially when there were indoor combustion sources presented. The indoor air pollution can be partly from the outdoor air pollution during the infiltration or penetration. And at the same time, indoor air pollution is from the indoor emissions directly. So the first process, which means the outdoor air impacts on indoor air quality, has been studied for a long time, but the indoor emission impacts on indoor air quality was not well studied, especially for those stoves using chimneys. People thought that for stoves using chimneys, most of the emission smokes was vented outdoor. How can this affect the indoor air quality? So this is a process we call the indoor leakage or fugitive emissions from indoor combustion to indoor air quality. There were no data in this process prior to 2015 or 16. And when I did my PhD postdoc study in US, in EPA, we did some laboratory study measurements to quantify the fugitive emission fractions. We had some results, but we found that generally it was less than 5%. This is lower than our expected and lower than field observation. So one of the reasons we thought is because the laboratory study cannot well capture the leakage situation in real world. So recently we developed a new approach to measure the real world leakage in field conditions. And we did some field tests. We found a significant leakage of particles and also CO into the indoor air. And here is some very preliminary results. We found the high leakages for particles compared to gas. And for particles, in some cases, its leakage can be as high as 40% or so compared to the 5% found in the laboratory conditions. So we think the leakage is one of the important reasons causing serious indoor air pollution. At the same time, we did many indoor air measurements. We're using the stationary samples to measure indoor air pollution, or we're using the personal samples to measure personal exposure. We found that this is the results of the personal exposure. Daily exposed to PM2.5 for the rural population was around 180 micrograms per cubic meter. Of course, this ranged from 10 to nearly 1,000. This is, some people were very strange to say, oh, they are surprised that it was so high. But not only our measurements, but many literature results, data also confirmed the high exposure to particles in the rural areas, especially those using solid fuels. This is a paper that published 2 years ago in Lancet Planetary Health. This is a study from 9 countries around the world, and they found that, for example, for particles in kitchen that could be as high as 300 micrograms per meter for those burning grass or animal lungs. And even for those burning gas or electricity, the kitchen PM2.5 concentration could be around 50 to 70 micrograms per cubic meter. So of course, there are very significant temporal and spatial difference, and there are very high intra-people variations. This is due to many factors like stove conditions, air exchange, and personal behaviors. We saw that if we using the improved high-efficient biomass stoves, it decreased the exposure, but this type of stoves was not used in a large scale. And for those using gas or electricity, their exposure level was relatively lower compared to the others, especially using the traditional solid fuels. But it's still very high, as I mentioned in this study. Their kitchen concentration was still around 50 to 70 micrograms per cubic meter. That was high above the WHO guideline. So we also saw some interesting results about the small particles. As I mentioned, the emission from the solid fuels was very small. So we have some results about the submicro particles, not ultrafine particles, and also the particle phase organics. We can see that people in these homes exposed to high levels of ultrafine particles and submicro particles. This is just one result we published that in yesterday later. We say that especially in those in winter, people have very high exposure to the PM1 during the heating or cooking process. And this slide that I'd like to mention, when I talk about the indoor air pollution or emissions from the solid fuel combustion for cooking and heating, some people ask me about the cooking oil forms. Our study did not cover this part, even though I know this is another source contributor to indoor air pollution. Its contribution to outdoor air pollution was very small. Some studies showed that the cooking oil forms contributed to less than 5% to 25% of outdoor air pollution, but it's directly contributed to indoor air pollution. But the relatively contribution will be different due to you using different materials, different oils, or different cooking method. Our study so far did not cover this part of the indoor source. So this is my last slide. I'd like to end with this. We study the residential household energy because it's directly related to the SDG 7, affordable and clean energies. But it's also related to the other indicators like health, climate change. Like I said, black carbon is one compound concerned in climate change, and residential emissions is one important source of black carbon. Of course, it's related to other indicators like land use, the equality, and education. So thank you very much.
Okay, thank you very much for the very excellent presentation, Guofeng. Really very good works. And I know you and your group have bridged the gaps, bridged the connections between the human activities and the energy transition, and also the climate change, and also human health. Very nice works. So any questions? I know Dr. Yang, your question, please.
Hello, Professor Sun.
Hi, I saw your question in the chat.
Yeah.
Yeah.
I wonder, can we quantify the reduction of energy consumption since the double carbon actions started?
Well, many people talk about the carbon emission reductions, but for residential, in fact, the contribution of residential emission to the total CO2 is less than 10%. So it's not a big contribution to the carbon emission. Of course, even though it burns coals. There would be, if we include black carbon or other climate forces into the estimate, we may see some more significant climate impacts from the residential emissions. But if only CO2, its contribution was relatively small compared to the current consumption in other sectors.
Okay, I know. So it is not so necessary to shorten the electric power usage for the residents.
Yeah, if you change to electricity, it may be increase a little bit about the carbon emission.
Mm-hmm. Okay, thank you.
Thanks for the answers, and also a question from Dr. Jin. Yes.
Okay.
Can you see the questions? 3 questions from Dr. Rongjin.
Yeah, I can see that for the measurement of PM 2.5 influence. Not only
about the emission factors.
Yeah. Okay. Yes, you are right. There are many factors can influence the particulate matter emission factors. So this is one of the reasons that at the very beginning we did the emission measurement in laboratory conditions, and then we found that the laboratory condition cannot capture all the conditions in real world. So we go to the real world to measure emission factors. One of our purposes is to get the reliable emission factors for emission inventory. So to do this, we do emission measurement in field conditions. But if we want to know how these factors affect or influence the PM 2.5 emission factors, we did some control experiment in laboratory conditions. So far that we have some very general results about how factors affect the emission of PM 2.5. But as you mentioned, it's very complex, and we need more work to see that which is the most significant factors. The second question is that the different combustion conditions leading to different composition. Yes, so well, in our results, we did not see any, we saw some correlations, positive correlation between OC and particular pHs, but we only analyzed the OC, EC, and pH. For some samples, we analyzed the pHs. We do not have a full characterization of particle compositions. There are some studies that are ongoing that try to establish emission source composition profiles that will be covered as many as possible chemical compositions in their studies. Okay, leakage of pHs. That's a very good question that we did not have these results. We have some work about the pH and VOC leakage into the indoor environment. So, but I do not have any data now.
Okay, thanks. The last question is from Dr. Qin. The question is about are there any other difference between the UFC and the PM 2.5? Are there any difference on the types of pollutants or
I guess there will be different. They will have different chemical abundance and including organic or inorganic ones. So they are different in not only size, but also their surface areas and combinations. But I do not have data on this.
Okay, thanks very much. Thanks again for your excellent presentation, Dr. Guofeng. Now let's move to the last presenter, the topic from Dr. Li Liang from Research Center for Eco-Environmental Sciences. The title is Environmentally Persistent Free Radicals in the Environment and Their Correlations with POPs. Please welcome Dr. Yang, please.
Hello, everyone. I'm Li Liang from the Research Center for Eco-Environmental Sciences, Chinese Academy of Sciences. And my topic is about new pollutants, that is the environmentally persistent free radicals and their correlations with the persistent organic pollutants. The outline mainly includes the background of the environmentally persistent free radicals, their characteristics in the atmospheric particles and their correlations with the POPs, industrial POPs. So environmentally persistent free radicals are emerging organic pollutants. The concept of the persistent free radicals were proposed relative to the traditionally concerned short-lived free radicals like the hydrogen radicals. And the persistent free radicals, short for EPFRs, were firstly proposed and discovered in the Secretariat since 1970s. And because of the limitation of the temporal technology for the detection of free radicals, the EPFRs acknowledgement on the EPFRs is proceeding slowly. But these years, the EPFRs is of increasing concern. Some studies has proposed that some phenoxy type radicals, that is the EPFRs on the PM surfaces, can exist for several days or even months. This is because the organic free radicals can be stabilized on the surface of metal particles, and this complexity containing the metal oxide particles and the organic free radicals can enter into the human body and induce the formation of the active reactive oxygen species formation, and then further cause the DNA damage. So considering the toxicity of these emerging pollutants, the EPFRs, their characteristics and potential sources and even formation mechanisms needs further attention. So in this study, we firstly explored the distribution characteristics of EPFRs in the atmospheric PM particles. We can see from these figures that the EPFRs will dominantly exist on the surface of 5 particles. Their concentrations in the particles of diameters lower than 1 micron were about 3 orders of magnitude higher than that in the particles of diameters lower than 1 micron, higher than 1 micron. And the EPFRs concentrations can increase along with the PM 2.5 concentrations, indicating the particle-dependent existence of the EPFRs. We can find that the EPFRs concentrations in the particles collected during the heating period and the non-heating period were quite different. The concentrations of EPFRs during the heating period were about 1 to 3 orders of magnitude higher than that collected during the non-heating period. And T-value is an important parameter for the identification of EPFRs species. And we can see that the species of the EPFRs collected during the non-heating period were relatively higher than that collected during the heating period, indicating that the oxygen-centered radicals were dominant in the particles collected during the non-heating period, and the carbon-centered ones were dominant during on the heating period samples. That can be easily explained that the non-heating period samples were collected in summer, and the higher atmospheric oxidizing capacity in summer can accelerate the oxidation reactions, then further induce the formation of the carbon-centered EPFRs. And the principal component analysis also indicated that the ozone concentrations as well as the temperature and the humidity were dominant influence factors for the EPFRs species. A multiple linear regression model was established in this study according to the EPFRs concentrations on the PM samples collected across the whole year in Beijing, China. And we can see that the ozone concentrations, the precipitation, temperature, and humidity were all important influence factors for the EPFRs concentrations. And according to this model, we can predict the EPFRs concentrations on the particles. We can see that we can predict the EPFRs concentrations without the direct detection by the electron paramagnetic resonance, and only according to these parameters. We can see that the prediction data agree well with the experimental data. And the EPFRs in the environment can be emitted from the thermal-related processes, just like the POPs. And we can see that in spite of their own toxicities, the EPFRs can play an important role for the formation of our concerned dioxins. We all know that the dioxins are of widely recognized formation mechanism. That is, the PCDDs can formed following the ER mechanisms by the radical molecular interaction, and the PCDFs can be formed following the LH mechanism with the radical interaction. But the current formation mechanisms are mostly speculative according to the distribution patterns of dioxin congeners from the practical sources. The detailed molecular formation mechanism of dioxins are still not clear, especially the free radical intermediates were not clarified yet for the direct evidence for the proposal of the dioxin formation. So the coloration of free radical intermediates with the POPs is the dominant, is focused concerns we focused, is the concern we focused. And considering the different distribution patterns of dioxin congeners from the 14 sources we investigated, we found that the current formation mechanism of dioxins cannot explain this huge difference. So we firstly used the high resolution gas chromatography or B-trap mass to screen the organic pollutants from different sources to clarify their distribution characteristics. And we can see from this figure that the benzene derivatives with chlorine or bromine substituents, which we are mostly concerned because they are the typical precursors of the POPs. And they dominantly exist on the surface or in the fly ash from the secondary copper smelting processes, and can be barely detected in the fly ash from the secondary aluminum smelting processes. And differently, as for the pH and halogenated pH in fly ash samples, the pH of higher rings and lower halogen substituents will dominantly exist in the secondary aluminum smelter processes. But on the contrast, the pH of lower rings but higher halogen substituents were dominant in the fly ash from the secondary copper smelting process. So it can be seen that the distribution pattern of the typical organic pollutants were quite different from different sources, especially between the secondary copper smelting processes and the secondary aluminum processes, quite different and even be opposite. So according to these differences of the distribution patterns, we proposed the potential formation mechanism of pollutants from different sources. And we can see that during the secondary copper smelting processes, and the halogenated pH of lower rings were dominant in the final products. And under the catalysis of the alumina, that during the secondary aluminum smelting processes, the pH of higher rings and the lower halogen substituents were dominant in the final products. But this formation mechanism is still speculative. The free radical intermediates have not been clarified. Our previous studies have do some tentative experiments and found that the metal compounds play an important role on the EPFRs formation and the stabilization. Under the catalysis of different metal compounds, we found that the EPFRs species, their concentrations and even lifetimes were all different. And these different EPFRs may further contribute to the difference of the organic pollutants formed under the catalysis of different metal compounds. So given the above, we would like to clarify the free radical intermediates. So we conducted the laboratory experiments to simulate the thermal-related processes. We used the in situ electron paramagnetic resonance detection for the detection of organic free radical intermediates. The devil-in cavity can ensure the temperature of the formation of the EPFRs formation, and we used the tubular furnace for the simulation of the thermal-related processes, and used the GC time of the gas chromatography time of flight mass spectrometer for the screening of the final products. We used the typical precursor of the POPs, that is the PCP, the pentachlorophenol, as the precursors to explore the catalysis mechanisms of different metal compounds on the formation of different mechanisms, and use the in situ detection combining with the DFT calculations for the deconvolution of the spectrum to clarify the multiple organic free radical intermediates, and finally use the time of flight mass spectrometers for the screening of the final products to clarify the different organic pollutants characteristics under the catalysis of the different metal compounds. So the line of the catalysis pathways on the different metal compounds can be connected by the in situ detection and the final screening. So we are the first to apply the electron paramagnetic resonance spectrometer for the identification of organic free radical intermediates during the formation of persistent organic pollutants during the thermal-related processes. And we can see that we use the theoretical calculation for the Happy splitting coupling constant, that is short for the A value, for the gas structure of the potential free radical intermediates. And so finally, we complete the deconvolution of the complex EPR spectrum. We also use the time of flight mass spectrum for the screening of the final products, and found the 4 tetrachlorinated dioxins was a dominant product. So according to the free radical intermediates we identified and the molecular intermediates we screened out, we proposed the molecular mechanism of dioxin formation, and the final products were also verified by the high resolution gas chromatography combined with the high resolution mass spectrum for the identification of the final products. So we firstly used the in situ detection of the free radical intermediates to provide direct evidence for the proposal of the molecular mechanism of dioxin formation. According to the methodology for the dioxin formation, we also detected the organic free radical intermediates on the different metal compounds. And from this table, we can see that under the catalysis of different metal compounds, the EPR spectrum were quite different on the different metal compound catalysis, indicating different catalysis mechanisms for the free radical intermediates on the different metal compounds. We can see from the figures that under the catalysis of the zinc oxide, the pentachlorophenol radicals and the lower chlorinated semiquinone radicals was the dominant free radical intermediates, but differently as in the copper oxide catalysis system, the chlorinated phenoxy radicals were the dominant free radical intermediates. All the free radicals detected in the copper oxide system was the phenoxy radicals. So from the theoretical calculations, we found that the hydrogen abstraction from the PCP is bearless and preferentially act as the first step for the formation of free radical intermediates. But in the copper oxide system, the free radical intermediates were active enough to interact with each other for the formation of organic pollutants. But under the catalysis of the zinc oxide, the formed pentachlorophenol radicals were relatively stable and can have enough time to be dehydrogenation to be the lower chlorinated phenoxy radicals and be oxidized to the formation of the semiquinone radicals. And different with the zinc oxide and the copper oxide catalysis system, the species and the concentrations of EPFRs were highest on the aluminum surface. We found that the methyl substituted free radical intermediates were the unique free radicals only found in the aluminum system. So we can conclude that under the copper oxide catalysis, the pentachlorophenol radicals were dominant, and under the catalysis of the zinc oxide catalysis, the phenoxy radicals and the semiquinone radicals were the dominant ones. And in the aluminum system, the specific methyl substituted phenoxy radicals was the dominant free radical intermediates. So given the above, we proposed the formation mechanism of free radical intermediates on the different metal compounds. We can see that the pentaphenoxy radicals can be easily formed under the catalysis of copper oxide, and then can be dechlorination for the formation of lower chlorinated phenoxy radicals. But under the catalysis of zinc oxide, the pentachlorophenol radicals can be further oxidized for the formation of semiquinone radicals. The vacancy can be easily detected on the surface of zinc oxide. So the easily formed vacancies can further accelerate the oxidation reactions for the formation of semiquinone radicals. But for under the catalysis of aluminum system, the pentachlorophenol radicals can be dechlorinated to the formation of lower chlorinated phenoxy radicals, and then through the alkylation reactions to form the unique methyl substituted free radicals. We also used the time of flight mass for the screening of the organic pollutants under different metal compounds. And this Venn diagram shows the identical and the discrepant organic pollutants from different metal compound catalysts. We can see that the OCDDs and the soil intermediates were only detected in the copper oxide system. Under the catalysis of the copper oxide, the high chlorinated products was the dominant product. And so the high chlorinated benzene and the phenols were also detected in this system. So the higher chlorinated phenoxy radicals can be dimerized to the formation of OCDDs and PCDEs. But as for the zinc oxide, the oxidation products was the dominant products in the zinc oxide system. The result is in accordance with the free radical intermediates we identified, that the semiquinone radicals can be further oxidized to the formation for those oxidation products. But as for the aluminum system, both for the alpha aluminum and gamma aluminum, the significant chain growth will happen. So the pH of higher rings but lower chlorination, but lower halogen substituents were detected in the aluminum system. This is a clear pattern of the organic pollutants under different metal compounds. We can find that the chlorinated products will dominantly exist in the copper oxide and the zinc oxide system compared to the aluminum system, especially for the copper oxide. And as for the oxidation products, the zinc oxide catalyzed the formation of the most oxidation products, and the alkylation products will dominantly exist in the aluminum system compared to the zinc oxide and the copper oxide. So the mutual verification can be achieved by the in situ detection of the free radical intermediates and the screening results by the time of flight mass. We can conclude that under the catalysis of the copper oxides, the highest the organic pollutants are of highest chlorination degree, and under the catalysis of zinc oxide, the organic pollutants are of highest oxidation degree. But under the catalysis of alumina the organic pollutants were of highest alkylation degree. So according to the in situ detection of the free radical intermediates and the final screening of the final products, we concluded the mental catalyzed the formation of organic pollutants intermediate by the organic free radicals. Under the catalysis of the copper oxides, the pentachlorophenoxy radicals can be dimerized for the formation of PCDE, and then the PCDEs can further be oxidized for the formation of OCDDs. This is the OCDD and PCDE were only detected in the copper oxide system. The result is in accordance with our previous studies that the copper oxide and the copper chlorine was the most effective catalyst for the formation of dioxins. So during the thermal-related processes rich in copper oxides, the dioxins need to be paid much more attention. And under the catalysis of the alumina, the pH of ring of higher rings can be detected. And we found that the alumina can accelerate the chain elongation, and so accelerate the formation of pH of higher rings. So during the thermal-related processes rich in the alumina, the pH of higher rings need to be paid much more attention. And in addition, I speculate that in the atmosphere rich in the alumina, the chain elongation may be occurred and further accelerate the formation of the concentrations of PM. So this will be the further investigation we will be conducted in the future. And under the catalysis of the zinc oxide, the oxidation products was the dominant products because of the strong oxidation capacity of the zinc oxide. So the result can be mutually verified by the practical results we conducted in the actual electric arc furnace they're making and during the secondary alumina smelter processes that with the raw materials rich in alumina. And we found that during these processes rich in alumina, the alkylation reactions can be accelerated, and so halogenated pH of higher rings can be found. And we can see from the congenial pattern that when we use the steel scraps as a raw material containing the organic impurities rich in the alumina, the pH of higher rings can be found in the practical processes. So field studies and the laboratory results can be mutually verified for the catalysis mechanism of different mental compounds on the organic pollutants. That's all my presentation. Thanks for your listening.
Recording in progress.
Okay, thank you very much for your nice presentation. And this is very new research about the formation mechanism of organic pollutants. It is about the free radical pathways for POPs formation. And I see a question is, you used for metal oxides in your experiments. Why did you choose those 4 metal oxides?
Thanks for the question. And we dominantly choose the 4 catalysts because firstly, these mental compounds were collected according to the practical industrial processes, because the dominant industrial industries we concerned was secondary smelting processes that rich in the copper oxides, the aluminum, and the zinc oxides, and so on. And these 4 dominant mental oxides catalysis mechanisms can answer the question that the different distribution patterns of the organic pollutants during those practical industries. So we choose these 4 mental compounds.
Okay, thank you for the answers. I have a question. During your experiments, and metal oxides catalyze the very different free radicals. So the interaction between the heavy metals and the free radicals might be very important and different. What is your opinion about the what is your idea about the interactions between the heavy metal, the metal oxides and the free radicals?
The interaction between the metal oxides and the free radicals, we have calculated the interactions and found the zero hyperphi coupling constant were very low. So the interaction between the free radicals and the mental compounds were very weak. This is the first one. And secondly, but the mental compounds can make important role for the stabilization and the formation of the free radicals, because under the catalysis of different mental compounds, the free radicals concentrations and lifetimes were quite different. So even though the interactions between the mental compounds and the free radicals were very weak, but they also play very important role on the formation of organic free radicals.
Okay, thank you. Hello, Zoe. I think it's time to end our free webinar here. Today we have 3 speakers and give us very excellent presentation. And any other questions or comments from Roland or Zoe?
Yeah, maybe one question to Lily. You know, in our 2001 papers, we very much highlighted the degradation of the soot matrix for the formation of the furans, where you do not really have, I think, much phenol or condensation involved. Are you, and now let's say in your presentation, you have mainly shown for the dioxins and the phenols as a precursor, yeah, which is of course also a part of the formation pathway. but are you also considering this kind of degradation of the larger soot particles and PAH particles with your radical mechanism? I mean, have you started with these materials, for example, on model fly ashes?
Yeah, the model fly ashes. We here didn't use the model fly ash as the reaction matrices, but we used the simulation matrices containing the metal compounds and the silicons. But we have detected the free radical signals in the actual fly ashes. But because the fly ash is very complex, the EPR spectrum is very hard to deconvolution. So it's harder to clarify the specific free radical species in the actual fly ashes. Yeah.
Yeah. Okay. And I mean, I started my PhD with the fluorinated phenols and fluorinated dioxins and furans. And my advantage there was that the fluorinated phenols are very stable. And therefore, it was very easy, let's say, to link the produced dioxins and furans. And let's say, first, I understood by this condensation reaction, because I synthesized all 210 different dioxins, fluorinated dioxins and furans, then this mechanism. And in the beginning, I also did not consider that these are radical mechanisms. But when you see in my 1998 paper, finally it was clear that these are radical. And finally, I also analyzed these dihydroxy precursors. So at the moment you are dealing with the chlorinated, have you ever thought on, let's say, doing some studies with fluorinated phenols?
Yeah, I think this is a very good direction. And in our further study, we can detect as this precursor detects the free radical intermediates and further clarify more the detailed formation mechanism of more persistent organic pollutants. Yeah. In this study, we dominantly clarified the dioxin formation mechanism under the catalysis of a certain precursor. Yeah.
Thank you.
Thank you.
Okay, I would like to say again, thanks to all the three speakers, Dr. Roland and Dr. Guofeng and Dr. Lili. And we also appreciate the support from the KeAi Publishing, and thanks for Zoe for supporting this free webinar. And finally, thanks to all the audience. Thanks for your attention. Okay, see you. Bye bye.
I thank you.
Any others from Zoe?
No, nothing from me. Thank you. Thank you for the chair, for all our speakers, and for the audience to stay for 2 hours with us. Thank you.
Okay.
Have a nice weekend.
Good progress with all your research.
Thank you. Bye bye.
Bye bye.